There are a number of technical safety challenges that need to be addressed to produce safe, highly automated vehicles. A significant challenge is building acceptable perception and prediction systems, and in particular, ensuring the safety of machine learning-based functions that are often used to implement perception and prediction. It's likely that more than simple object motion tracking will be required for many of these automated vehicle applications. Consider, for example, this deer at the side of the road. The deer is currently standing still, and a motion tracking-based predictor would say, well, it's still now and it's going to remain still. But any experienced rural driver knows that the thing that happens next is the deer waits till the car is almost on top of it and then runs in front of the car. A prudent driver would realize that this is a highly risky situation and would reduce vehicle speed when approaching the deer based on the prediction that the deer is likely to run in front of the car. This kind of sophistication in object classification and being able to hypothesize what happens next will require a high degree of sophistication and will also apply to urban situations in which there are pedestrians on the edge of a sidewalk. An ability to ensure that predictions are robust enough to achieve acceptable safety remains a significant challenge in the field. Another technical safety challenge is properly executing a safety of the intended function SOTIF design process. A simplistic version of SOTIF is to drive, find a problem, fix it, drive some more, and iterate until you have lots and lots of testing miles on real-world conditions. For example, Waymo has said they've done 6 million test miles, but only 65,000 deployed miles. If you're testing orders of magnitude more miles than you're deployed, then you can make an argument that the testing will have seen pretty much everything that is likely to happen during those few miles of deployment. But to deploy at scale, at some point, you'll need to have real deployed miles beyond the number of real-world test miles. Sure, simulation can help to a degree, but only if the simulation and the scenarios in the simulation and the objects in the simulation can account for all the things that are likely to happen in the real world. An issue that is not addressed by this set of standards is, how do you know when you're done identifying weird things that will happen in the real world and it's time to deploy at scale? Answering that question for large fleets is likely to involve UL 4600 concepts and safety cases that go beyond, here's what we've seen, let's deal with it, and argue to completeness that all the likely hazards have been identified and addressed, whether or not they were seen in system-level testing. At a higher level, a significant technical safety challenge is getting from works okay to safe. You can brute force your way into the first few nines. And by that, I mean, if 99% of the time your perception system works, you can do that by brute force testing. But you can't get all the nines you need. You can't get from 99% to 99.99 bunch of nines to life-critical number of nines. You can't do that with brute force because it's simply too expensive. You'll need to use some sort of simulation-based effort and then apply an argument that the simulation actually gives you the number of nines and all the other parts of positive trust balance. Especially, you'll need field feedback into safety cases to know that you've deployed safely at scale. Even after you've done all the engineering rigor and validation that you think is required, you'll also need field feedback based on your safety case to ensure that your safety case is valid and that you notice and respond to changes in the outside world that were not considered at design time.